All right, y'all, so this is the last video for Unit 2, and what we're going to do is I'm going to do some things where I'm going to repeat some things, just kind of reiterate some things, go into a little more detail, and then add some transformations on here, so new concept. I would say you probably don't need to watch these AP videos, maybe nonlinear transformations if you have questions what I'm doing here on the calculator. All right, so in the last lesson we talked about computer outputs and how we're not going to use these in our class, but you need to be able to read them on the AP test. So I'm just going to go over these again, just because it's important that you understand what all these terms are, because they don't always, they're not always very clear. So whenever we see constant on here, we know that we don't actually know the context of the problem, but we know that this constant is always going to be our y-intercept. And that's going to be, I'm going to assume here that everything we're going to do is the a plus bx formula, right? So that we're going to use this model, the stats model, and our intercept in this case is going to be our a value. We also know that the constant here, because it's the intercept, this is our y. And here we're going to know what the x variable is. So whatever the context of this problem is, we know that the x variable here is going to be age, and then the value that we have here, 2.11, this is going to be our slope. All right, so what else do we know on here? We've got this value of s, and this is not just the standard deviation. So this is the standard deviation deviation of the residuals. So that's super important. So just kind of a little review here. Just do this on this paper. If I had s of x, this would be the distribution. So here I would have the standard deviation of a sample set, so uppercase sample set, in the x direction. So my x direction, or my x variable. If I had s sub y, this is the standard deviation of a sample set of my y variables. And we know we're going to use s sub y and s sub x when we calculate our slope formula. Now, this is different than if I had sigma or sigma x, sigma y. If I had either of these, then this is the standard deviation of a population. So population, big sample set, standard deviation, small sample set. Okay, so this is big, this is small. And so when we see just this little s here, we know that this is the standard deviation of the residuals. And so what this is, just to kind of review what the standard deviation of the residuals is, the larger s means that we have a larger residual. And remember, the standard deviation is the difference above or below the mean. So if we have this larger residual, this means we have more variation within our residuals. And so what this does, it's the y value here, it's the units of this y value that are going to predict our error. So how much error do we have in our least square regression line? That's what this is saying. Okay, we have this r squared value that's right here, so my r squared value, and this is the coefficient of determination. This is almost always given as a percent. And just a little review, that if I want r, the r value here, this would be the square root of r squared. So my r value is the square root of r squared, and this gives us our coefficient of correlation. In fact, let me do a little review on these two as well, because I think it's important. So if we look at what r is, so we just said r is our coefficient of correlation. And so when we calculate this r, what we're really doing is we're measuring the strength and the direction of our association. So this tells us, this R value tells us if we're positive or negative and how positive or negative it is. So if I had a value like negative 0.97, this tells us that it's a pretty linear representation. It's almost -1, and it's in the negative direction. So I would have something that looks pretty linear in this direction. All right, whereas my R squared value, so this is going to measure, MEAS, measure how much variation our best fit line or our least square regression line has in the y direction. So how much variation in the y direction. All right, so if we look at this case, we have 95.4. This tells us that 95.4% of the data is accounted for with our least squared regression line. Okay, so this tells us the variation versus R, which tells us the strength and direction. So it's important to understand the difference between these two. All right, okay, let's get back up here. So what you see in this red box, this is all, these are all values that we're going to use, but we're not going to use those until we get on to Unit 9. And then in AP Stats, we never use the adjusted R squared value. So just make sure you're using R squared and not R squared adjusted. Okay. Let's see, what do I have here? Standard deviation of the residuals, so we're going to use that more in Unit 9. We can interpret it here. That's what this is. Okay, let's go back and talk here a little bit about our S value. So what happens is, when we look at this value, we don't know if our standard deviation of 0.971 is good or bad. We don't know that. We don't know, in this case, the context of this problem. And that's what this is saying. If we had a standard deviation of residuals that was 100, it would be large if our Y values were trying to predict age in years. So if we had 100 years as our standard deviation of our residuals, that would be huge. But it would be really small if we were predicting age in seconds. So we can't look at this value of 0.97 of our standard deviation of our residuals and know that that's a good value or a bad value. We can look at our R squared and say 95.4% encompasses the majority of our variations, so this would be a good model. But we can't tell anything from this without knowing the context of the problem. Okay, so based on this, I have my y-intercept, I have my slope, so I can create my least square regression line from this data. So what I would have is y hat, because it's a prediction, and I have my constant, which is 3.371. That's my y-intercept. My slope is positive, so I'm going to add 2.114x. So this is my least square regression line, which I can pull directly from this. We did this when we did the manual calculation, where we can go back and look at this. But if you're just given a table and it's not asking you to calculate it by hand, don't do it. Just plug it in. Now, we said up here what our R value is. So R is going to be the square root of 0.954. So remember, when we do this, we're not using the percentage. We have to convert this to a decimal. So we have 0.954. And when I plug this in my calculator, let's see what I get. Square root of 0.954, I get 0.977. So in the context of this problem, this says that we have a really strong strong association, so we're very close to 1 in the positive direction. So we would say that this would be a strong, linear, positive association. Okay? All right, so let's talk more about influential points. So an influential point, this term of influential points, is what we're going to talk about when we talk about outliers. So when we're looking at our two variable data, we could have more than just an outlier. We can have something that we call a leverage point. So an influential point in the data set is a point that has leverage on the correlation and the regression line. So what this basically says is if we took a point out, what would happen to our standard deviation and our coefficient of determination. And so here's kind of what this looks like. So if I had a graph and I had this association that looks like this, and I have these 2 points right here. So as I look at these, points, I could say, okay, this point might affect the data, and this point might affect the data. So how do I know what is what? All right, I think I have some definitions over here. I do. Let's pop over to do some definitions really quick. So if you pop over to the other side, go down here at the bottom. So what I have here are points with high leverage, have a much larger or much smaller x value than the other points in the data set. Okay, so if we go back and look at this little graph that I have here, this point, here's where my x values end, but I have this one point that's hanging out here. So this variable that goes, I have this distance here, basically I have a gap. This would be a high leverage point. It's way out there compared to where the majority of my data is. Okay, so that would be a high leverage point. An outlier in the regression is a point that does not follow the data and has a large residual. So let's go back here. This point would be an outlier. So what happens is, if I look at my best fit line, and my best fit line looks like this high leverage point falls on the best fit line. But when it falls on the best fit line, it's away from the majority of my X data, so we call this high leverage. This point does not fall on my best fit line, and it has a large residual. So because it has a large residual, we're going to call this point our outlier. So what we then have are this concept of influential points. So an influential point in a regression is any point that, if we take it out, substantially changes the slope, the y-intercept, the correlation, the coefficient of determination, and the standard deviation of the residuals. So bottom line is, influential points are all high leverage or outliers. So when we talked about distributions of data with our one variable data, so everything that we did in Unit 1, we would have said that this guy's an outlier. He's hanging out over here because he's going to skew the data one way or the other. It's different when we talk about two variable data. So two variable data says, okay, we have this gap that we have, so we have this point out here that could skew our data. It's going to change our data. For sure, an outlier is going to change our data, and that is just away from our least square regression line. Okay, so let's look at this in terms of this little example. So I have no context on this, but let's go ahead and put this data in. So you have L1 and L2. So I'm going to also put this data in because I don't have it. Okay, so 1. Okay, so I have this data, and I need to make sure my stat plot's on. I've got to change something in my stat plot, but in your stat plot, remember, it needs to be on, it needs to be on stat plot, and you need to have your list 1 and your list 2. So I went through a lot of calculator commands. If your calculator is not set up, you can slow this down and look at it again. I want to look at the data, so I'm going to do zoom stat 9. Oh, I want to get rid of that line there. It's from something else. Okay, here's what I have. So I'm going to just draw this scatter plot, and I have something that looks like this. And so if I look at this data, I could, it's easier for me to see on my calculator. If I did a best fit line, okay, maybe this guy, right, and maybe this guy, I don't really know. Let's just, if I draw my line that looks like this, I would say that probably if I have a point that is influencing my data, it's probably going to be this one, okay? Because it's got the largest residual from the graph. And I drew this point pretty low here, but on the calculator it looks like it's much closer. Okay, so now I want to run my least square regression. I want to fit my line on there. So I'm going to go to Stat, Calc, Linreg. Now I want to save my graph. So under Store Regression Equation, Alpha Trace, I'm going to save this as Y1, and I'm going to draw this out. So I'm going to go ahead and write my equation down. So what I have is Y hat equals, I'm going to write this in stats format, so 0.933 plus 0.971x. Now be careful when you do this, because I have the A and the B opposite because I did a standard slope equation. In fact, let me just redo that again so that there's no confusion. Okay, so my A value is 0.933, my B value is my slope, 0.971, and I want to know my correlation coefficient, so this is 0.777. Now, this makes sense. It's positive, it's pretty linear, so it's moderately strong, positive linear relationship. So I'm good with all of this, okay? So, hey, all right, this looks good, this value looks good, but now what we want to do is we want to remove this ordered pair at 2, 5, and we want to rerun our data. So this point's not considered an outlier because it fits the data, but we don't really know if it's an outlier. So let's check it and see if this becomes an influential point. So I go back to my data. I'm going to go down here to the 0.25. I have to delete the x value and I have to delete the y value. And now I'm going to rerun this. I'm going to go ahead and save this. Save this as line 2 and just kind of see how that changes the slope of the line. All right, so here's my new least square regression equation. I have negative 0.473 plus 1.229x. And my R value now is significantly closer, 0.914. So remember, the goal here is that our R value wants to be as close to 1. So removing this point at 2.5 pulls my data much closer to where I want it to be. So if I look at this, I've got this original graph that's right here. The blue line was my first graph. I take out that outlier and I have a new graph. So what we see happen here, and that's what the question is here, what happens to the slope? Well, because I have both graphs on the same plot here, it's easy to see what happens to the slope. So as I removed the 0.25, my slope changed. My slope went from 0.971 to 1.229. So what happened? So I removed the point, so my slope increased. And why did this happen? This is because that 0.25 had leverage over the data set. Now, be careful, because this point leverage that I have here is different than this high leverage. This high leverage tells you that you have a point that's way out there in X. But what happened is it modified the value of our slope. Our slope increased. So let's look at our y-intercept. So our y-intercept of my first line is up here. My y-intercept of my second line is down here. So the y-intercept decreased. So what we see, and this is the important takeaway, is that we have an inverse relationship between the slope and the y-intercept. So as we remove these influential points, what we're going to see is that our slope and our y-intercept are going to be opposite. This one increased, this one decreased. They have an inverse relationship. So what happened to the correlation? Well, that's what happened to the correlation. We have this inverse relationship. The correlation got closer to 1 because we removed an influential point. and that influential point was an outlier at 2.5. Now, remember, an outlier in this case is not an outlier like we saw when we had a data distribution. This outlier just means we have a high residual. So lots of vocabulary on that. So if you're struggling with vocabulary, go back and look at the AP exam, okay? All right, so that's everything that I wanted to talk about with outliers and data sets. So now let's go on to another concept in this, which is departures from linearity. And this is super wordy, but I want to talk about this real quick. I'm just going to actually read through this. So in our AP Stats course, we only deal with two variable data that can be modeled by a line, or nonlinear two variable data that can be transformed into a line. So everything that we do when we get this data, our R value, our R squared value, this is all because we have linear data. But we know that we don't always have linear data. We've talked about that in this section. So to know what transformation to use, we have to graph the initial data. We have to look at the scatter plot. The scatter plot may or may not show a linear pattern. It might look linear, but we don't really know until we graph the residual plot, and we have to see if the residual plot is random. If it's not random, we have to do a transformation. Okay, now here's the part that gets crazy. The transformation can happen on the independent variable, the dependent variable, or both. All right, here is the hard part. When you're doing this, it is completely random. Now, when I say random, what I mean is you really you have to do trial and error sometimes to know which type of transformation to use. And I'm going to show you an example of this today so that you can kind of see how sometimes it doesn't really matter, okay? So this says natural log transformation, and we're not just going to do natural log. So we're going to do both. So here's the context. The number of certain type of bacteria present in the thousands after a certain number of hours given is in the table below. So we have this number, and it's in the thousands after so many hours. So the first thing that we want to do is we want to just look at this data. We want to look at the data and see what happens. So I'm going to put the data in. So I go here, I'm going to modify this list. So go ahead and add this data. Okay, so there's all the data that I have. Go ahead and pause the video if you need to go a little slower. I'm going to create the scatter plot, so I want to go in and delete the lines that I just worked on those previous problems. And I want to go in and do, the other thing I have to do is check my list, L1 and L2, so I'm good. I'm going to do zoom 9, and here's what I have. So if I look at this data, it looks like this. So that absolutely does not look linear. All right. So, but I am going to look at my residual just to confirm that this is not linear. Okay. So remember what I do is I'm going to go second stat plot. I go into my plot and I go down to my list. What am I doing? And I have to go down and pick the residual. So my Y value now that's getting pulled is my X variable and then the residual. And I'm, oh my gosh, struggling here. Let me look at this again. I don't know why I'm getting an error here. L1, residual, stat. hold on, let me figure out why I have an error. I'll be right back. Duh, I know why. Hold on, I didn't run my regression. So I have to go down here and I have to run my linear regression, because what this is telling me is it's telling me my residual is from my best fit line. I don't have a best fit line, so duh. Okay, let me go ahead and save this just so I have it in case I want it. All right, so here's my equation of my line. And so my equation of my line looks like it fits pretty good, right? 0.959. So that looks like that's a pretty good best fit line. But when I look at my plot now, what I see on my residual plot is this almost perfect parabola, right? So what I know is that this is non-linear, and this is a bad least squares regression line. Okay? So let's go back to these questions. So it says, why is a linear model not appropriate? Well, the parent function looks exponential. E-N-T-I-A-L. It looks exponential. We saw this here. We could have assumed right from the beginning that it was exponential. We run the regression. When we run the regression, we get this type of residual plot, and we know that a parabola residual plot is bad. Okay, so we want to change this and make this look like from an exponential. We want to transform this. So how do we undo exponents? We take the log. So we can do log or we can do ln. And I'm going to show you both today just so you see that it doesn't really matter. Okay? And this is what I said here. You may need to do some trial and error to figure out which transformation to use. This is obvious, right? That this is going to be exponential, but it's not always the case. Okay, so normally it's going to give you a clue, but if it doesn't, you have to just use your algebra skills on what type of function you have. Okay, so we have this data, and so now we want to go pull the data here so that we can run different regressions. So what I have is, if I go back into my data, I'm going to go over to my list 3 this time, and I'm going to use natural log. So instead of calculating it and putting the data in, I'm just going to say ln of this number, 1.8. So I put the function right into that list, and what I get here is 0.5878. And if I do another one, I would have ln of 2.4, and this tells me 0.8755. Now, there's no really reason to fill out this table. You can if you want to, but what's important is the calculator will do it for you. So go ahead and do this. We're doing natural log for all of these. Okay, so there's that data. And now what I want to do is I'm going to do the same thing, but this time I'm going to use log. So instead of using ln in the calculator, I'm going to make it log of that value 1.8. So you see here on the calculator, it's now log of 1.8. When I hit enter, I have a different value, 0.2553. And if I do one more here, log of 2.4, this gives me 0.3802. So we can see that these values are different. And so don't freak out about that, because we're going to see what happens at the end. So go ahead and publish the rest of this table. So this next one is log of 3.1, log 4.3, log of 8, log of 14, and log of 18. Okay, 2 different data sets. Now, just so that I'm clear, this is my data set. My log data set is L4. My natural log data set is L3. Okay, so we have all the data. So now let's flip this over. We want to create a scatter plot between ours and natural log. So this is going to be between our L1 list and our L3 list. And then our log is going to be our L1 and our L4 list. Okay, so I have to run a linear regression. So I'm going to go back, stat, calc, go back and run our linreg. I'll go ahead and save this. Okay, so I have an equation. I'm just going to go ahead and write this down. I'm going to say my equation is y equals negative 4.27 plus 3.94x. So this is my new equation when I run a linear regression with my ln data. Let me say that again. I ran a linear regression with my natural log transformed data. Okay, so now what I want to do is I want to look at that scatter plot. So I have to go in here and change this. And so now remember I ran it with the L3 data. So I'm going to have to change that. And then I want to look at my data. And this is my new data set. Very linear. So my new data set, don't worry so much about that line, but my new data set looks really good, right? It looks like that. All right, now we want to run the residual. So I'm going to go back into my stat plot. I'm going to go down here to my data, and I'm going to change this variable to my residual. Okay, now I'm going to get rid of that line just because it irritates me, and I want to zoom stat so that I can see this. And what I have here, hold on, let me make sure I did that right. Residual. Okay, so what I have here is that I have this line that looks like this. Okay, let me go in now and look at my, okay y'all, so I paused this because I was saying in my mind that something didn't look right. So when we ran this scatter plot, we got this almost linear line, which is what we wanted to do. But when we ran the residual, it's still a parabola. And I was like, well, wait a minute, if this is linear, why does this look like a parabola? Well, I ran the linreg wrong. So if I go back to stat and I go over to calc and I go down here and run my linear regression, I was still pulling from list 2. And so I need to go in here and I need to change this to list 3. That's my LN data. So if I pull from list 3 and I run this, and now I look and I see that I have my L1 and my residual ID. So my residual is going to pop up now on my latest scatter plot, right? So my latest linear regression. And now I graph this. I want to change my view. I see that I have a random sample, which is what I wanted. So it doesn't look like a parabola anymore. I was pulling the wrong data set. So now I have something that looks more like this. So this is very random. And remember, what we have to have for us to have a good residual is we want something that's more random. So this looks good. So now let's go back in and run it again with our log data. All right, so if I go in here and I look at stat, I want to rerun this, linreg, and now I'm going to pull from list 4. That was my mistake a minute ago. So now I'm going to pull from list 4, which is my log data. Here's what I have. So I want to go in and I want to change this so that I have just my L4 data. Okay, here's what I see. So again, something that looks super linear. Now what I'm going to do is I'm going to go in and I'm going to look at my line. I didn't write my line down. I'm going to rerun this really quick because I want to write my line down. So my line here becomes y hat equals negative 0.002 plus 0.255x. Okay, I'm going to come back to that in a minute. So now I'm going to go back into my stat plot. I want to go down and I want to run my residual. And here's what I see. So if you look at where we were with the first one, with ln, and we look at where we are with the log, they look very, very similar. All right. So let's, I'm going to do one really quick thing since I made a mistake on that first. I'm going to rerun this with L3 just to make sure I wrote my equation right. So this is going to be y equals negative 0.004 plus 0.586x. Okay. Now, the reason why I wanted to rerun that is because you see if I ran it with an ln or I ran it with a log, I have two different equations, right? My slope here is 0.586. My slope here is 0.255. Okay. So let's look at this now. So why is this a better fit for our linear regression? So it doesn't matter which one of these I did, whether I did the natural log or I did just the log. This is a better fit for our linear regression because our residual plot is random. So I have random scatter. And my scatter plot looks linear. Okay. Now, it doesn't matter which one of these equations I use. So I'm going to show you something above. So if I have this regression equation for the transformed data, so this would give me y hat equals 0.255x minus 0.002. This is for my log data. And I have y hat equals 0.586x minus 0.004, and this is for my ln data. Okay, now here's why this is important. If I have this, I have to include this part of my equation because it's not a linear line. It is a linear line, but it's a linear line because we transformed it with log, or it's a linear line because we transformed it with ln. And so if I want to look at this data, right, if I look at these two datas, I have to tell it either log or ln. Okay, now what this is saying is, using the equation above, what would be the predicted quantity of bacteria after 3.75 hours? So the data that I have in here right now, let's go back and look at my graph. I want to put this back on a stat plot. So I'm going to change this. And I'm going to go down here, and I'm just going to say L3. So I'll use the linear data, the ln log data. And I graph this. Here's what I have. So let me run this so that I get my best fit line on there. So stat, calc, linreg. I want to store this. There's my equation. I'm going to go ahead and graph it. So here's what I have. I see that that line looks like it goes through there perfectly. If from my calculator I want to know what happens at 3.75 hours, I'm going to do alpha trace, second trace, and I want to find the value at 3.75. So what I get from my calculator is I get 2.192, and this value is going to be in thousands. So 2,192 bacteria. Now, if it wants to see how you calculated this manually, well, remember I ran my ln data. So what I have is ln of y hat equals 0.586x minus 0.004. This is my equation. Now, what I want to do is I have to make this just y hat. I have to get rid of this ln. So to get rid of natural log, we're going to use e. So if I e this and I e this, what I end up with is y hat equals let me do this. E to the 0.586 times 3.75 minus 0.004. So in my calculator, I can put that all in your calculator, or you could have just done this part and then do the E. So I'm going to do E to the 0.586 times 3.75 minus 0.004. And what I get is that this value of y hat is 8.960 thousandths of bacteria. Okay, now let's talk about this. So this number and this number are not the same. So why are these two variables different? Why are these two numbers different? And the reason for this is because when I calculated this on my line, this value that I have is before I've taken the ln. So I'm going to go back. Actually, I don't have it there. I'm going to go back and I'm going to say e to the 2.192, and this value, e to the 2.192, gives me 8.953. So if I do a comparison of these two numbers, they're super close, right? This value is my most accurate value because I've taken it straight from the graph that's been non-modified. I didn't round it, and this is rounded data. So the reason I showed you this is because it's really common for people to just look at the regression line, pull the value off the regression line, and say your answer is 2.192, right? But what we know is that this is a modified line. So if it's a modified line, I have to go in and do the opposite, which would be E. Now, the smart thing is we want to know what's happening at 3.75. So if I go back to my data right here, 3.75 is going to fall within this range. So if I know that this is a linear relationship, or I've changed this relationship, what we ended up was, 8.96? So this makes sense that between 3.5 and 4, because I've evaluated this at 3.75, that my value is 8.96. If I would have kept this value at 2, it would not have fit the data. So that didn't make any sense. Okay. All right, that was it. Go back and look at that transformation if you need to.